Hello, Professor Zhou. Hi, hello, Professor.
Hi, how are you?
Good, good. How are you?
Good.
So the only one is missing is Anton from the committee.
Oh. There's a lot of people there already. Great.
Anton. Okay, so Anton is here. Hi.
Yes, I'm here.
Hello, Professor.
Anton.
Sometimes I have problems with my sound. You can hear me, right?
Yeah,
Yes.
I can hear you.
But are we the only ones? Or there are more people coming?
Okay,
There are a lot of people.
should we start now?
Yeah, I think
Yeah,
so.
the committee is
There are
here.
a lot of people here. Okay.
Okay, let's start. Today's talk is given by Yinsong Chen. This is his thesis defense. Okay. The title is Counting and Sampling Ribbon Tiling of Rectangles. All right, let's start.
Okay. Good afternoon, everyone. Thanks for coming to my defense. So the title is Counting and Sampling Ribbon Tilings of Rectangles. So I'll talk about ribbon tilings. So here is basically the outline. So in the first part, I will talk about the definition of ribbon tilings, and especially I will explain a bijection with cyclic orientations. And using this bijection, it helps us understand and analyze ribbon tilings. So in part two, I'll introduce shortly some known results and maybe my interest. And part three, the main part is our contributions. And at last is some future work. Okay, so let's start. So first of all, what is ribbon tile? So ribbon tile, order n ribbon tile is basically a connect sequence of n squares, and in each step you can go either up or right. So you have only two choices, up or right. So here is an example of order 4 ribbon tiles. For example, the first one you always go up, and here you go up, and finally you go to right. So basically you need n-1 steps, and in each step you have two choices. So in total, you will have 2 to the power n-1 types of ribbon tiles. Okay. So this is the definition. So maybe another way to define it is to consider a two-dimensional lattice, and here is a square, and we can talk about the level and the color about the square using its left bottom corner. So for this square, we observe this point. So its level is just simply add the two coordinates x and y. So it's level, and its color is defined by its level mod n. N is the order of ribbon tiles. Okay, so basically for every squares, we have n colors, n possible colors for it. So maybe I need to. So this window doesn't hide you from my screen, right? So, yeah, okay. So okay. So for order n ribbon tile, is basically you can contain only one square from each color. Okay. So here is again an order 4 ribbon tile. So basically, these two definitions are equivalent. Okay. So and here is important. You can have only one square of each color. It's very important in the definition. Okay. Okay. So after define ribbon tile, I talk about what is tiling. So tiling, so basically, is a cover of a region using using these ribbon tiles. So here's an example. So basically, you just try to put the ribbon tiles inside this region in some proper way. Okay, and so we talk about the level of each tile is defined as the square who is in the lowest level. For example, this tile is level 0, this tile is level 1, and here is a tile level 5, and so on. Okay, so this basically is a tiling. And for tiling, we define a local move. So local move, for example, in this picture, we can take off this 1 and 2, and then put it back in the other way. So here we call it a local move. Okay, there's an important conclusion that ribbon tilings are algorithmic by these local moves. So basically, it means for any two tilings, they are connected by a sequence of local moves. Yes, I think Professor.
I have two questions. First, what's the number here? Is the number just the index for different type of tiling?
No, the number here is indicates it's a level. So here is a level 0 tile. Here is a level 1 tile.
What is the level?
Okay. So level, we define the level of each square, right, at the beginning of the define the ribbon tile, and then
So go back to the definition.
Okay, so here's the level of square. So for example, this shaded square is level is x plus y.
So it's basically L1 distance to origin, right? Sort of.
Yes, so it's L1 distance for its left bottom corner, yes.
Okay. So, okay, that explains my second question.
Okay. Okay, so maybe let's go on. Okay, so local movement is algorithmic, and then next is some motivation for us to study ribbon tilings. First of all, ribbon tilings has some connection with Young's table locks, so which is related to representation theorem in algebra. So there's one motivation, and the other motivation is come from domino tiling. So domino tiling is much studied for its connection with perfect matching, spanning trees, and the so-called dimer system in physics. And the ribbon tiling can be considered as a generalization of domino tilings. So domino tiling is just the ribbon tiling of order n equals 2. Okay, so here's some motivation. So next part, I will explain, the goal is explain the bijection shown in this picture. So on the left, you see it's a tiling, ribbon tiling. On the right is a cyclic orientation. So this S, we call it boundary squares. So here I just pick up one as an example. In principle, we have many boundary squares incident to the boundary of the region, but outside the region, but incident to the boundary of the region. So I only pick up one, otherwise the plot will be too messy. Okay. And for cyclic orientations, so this green line or dashed line doesn't matter. What matters is the shape of this arrow. So if it's a black triangle, it's a so-called false edge, and here is the other type of edge. So I think we have questions or something.
Yeah. Okay. Wait. So is that a complete graph? No.
No, not a complete graph.
There is an edge between two vertices if what?
Yeah, I'll talk about it later. I'll explain for more details later.
All right.
But definitely not a complete graph. Okay. So
I'd just to mention something. When you say acyclic orientation, you have to say of what? Specifically of graphs.
yeah, a cyclic orientation of these graphs. So this graph can be constructed, and I'll explain it later. So basically, the vertices corresponds to each tile and all boundary squares. Here, I pick up one for example.
I'm not talking about that. I'm talking about using the term acyclic orientation. When you say acyclic orientation, it could be of different things. It does not have to be of graphs. So you should say of graphs when you
yeah.
concept.
Oh, thank you to correct me. So it's a cyclic orientation of this graph.
The concept you have here is acyclic orientations of graphs.
Yes, yes.
A particular example is an acyclic orientation of this particular graph. So in your table of contents, you should say acyclic orientations of graphs, not just acyclic orientations.
Okay, I see. Thank you.
That's all. Okay, thanks.
Okay, thank you. I'll pay attention. Okay, so first of all, let's define a left-off relation. So we rotate the tiling 45-degree counterclockwise and observe from left to right. So for example, this tile 2, and we say it's on the left of 5 because its projection is inner. Is the inner point located the inner part of this tile 5. So we say 2 is on the left of 5. Okay, and the same thing for 3, and this boundary square S and the other 2. And for this one, 6, we say 2 and 6 are not comparable. So because here the projection is kind of on this corner is on the boundary, but not the inner side of this 6. So it's not comparable. Okay, so this is how we define the left-top relation. And here are some facts. So 2 tiles are only comparable when their level difference is less than or equal to n. For example, here n equals 3, and the 2 and 6 are not comparable since their difference is larger than 3. Okay, and the second item, you cannot have this relation hold together. So you can only have one tile is on the left, but you cannot have both on the left or the other way around. You can't have both. And maybe the third item, so the left-off relation is not a partial order because it's not transitive. So, but in principle, we can extend it, but I won't use too much argument about partial order. So it's okay if you ignore this. Okay, so this is what is the left-off relation. All right, so in this page, there is some strong conclusion from Sheffield 2002. Basically, it's talk about some invariance for all ribbon tilings. So all these properties does not depend on tilings. So first of all, the number of tiles in each level is invariant for all tilings. For example, in this plot, there are 2 tiles in level 2. So it doesn't matter how you tiling it. You must have 2 tiles in level 2, and 1 tile in level 3, 1 tile in level 4, and 1 tile in level 5. This is fixed. You have no other choices. It doesn't matter what tiling it is. Okay. So, and the second item, some left-off relations are fixed. For example, the tiles from the same level. So this 2 is always on the left of this 2. So this is 2, 1. This is 2, 2. But it's, so you can basically you label it this way. Okay. And this item may be more interesting. So if the level difference is n, then their relations are fixed. For example, this 2 and 5. So you will always have this 2, 1 is on the left of 5. So corresponding to the graph, you have a orientation from 2, 1 to 5 in this way. Okay, and this is fixed. It doesn't matter what the tiling it is. Okay, and the last one is the left-out relations between tiles and boundary squares are fixed. So for example, this S, it will always between these two. So 2, 1 is on the left of this S, and this S will be on the left of this 2, 2. So I also show it in this picture. Okay. So basically, you say the graph I put here, it doesn't depend on tilings at all. It only depends on this region. Okay. So maybe from here it's more clearly. So ignore the tilings. We only have this region, and we can construct this plot. Okay. We know there will be 2 tiles in level 2. So we liberate 2, 1 and 2, 2. So and so on and so forth. And we also have some false edges. The false edges means their orientation are fixed. And also some, this edge, we call it free edge. And we also know it because if their level difference is less than n, they will have a free edge. Okay, so if it's too large, for example, if you have 6, 6 and 2 are not comparable, so you don't have an edge between 2 and 6. Okay, so again, this graph is only depends on the region R. It doesn't depend on tilings. Okay. So what if we put the tilings here? So if we put a tiling in this region, we will basically have some orientation on these free edges. For example, 2 is on the left of 3. So you have from 2, 1 to 3. Okay. So this tiling determines this the orientation of the free edge, and the other way around also holds. So the acyclic orientation of this orientation determines the left-out relation in the between tiles. Okay, and you can check this one is acyclic. Okay. So and this picture is a picture we saw previously. So I explained this bijection. So between ribbon tilings and acyclic orientations of the graph. Okay. Okay. And moreover, we talk about local move between tilings. And so local move is just add flips. It's also bijectively correspondent. So for example, here we have from 5 is on the left of 3. So 5 to 3. And here it's a local movement. We put it the other way back. So 3 is on the left of 5. So basically, we just flip the direction of this edge. Okay, so any questions?
Good question.
Yeah, so are you saying the gray arrow is left off? And how about the other type, the triangle one?
The gray or dashed line doesn't matter. It's just show this picture, try to show this picture more clearly.
I mean, not gray, I mean the gray arrow, this other kind of arrow, not the,
this one, you mean? Okay. Yes, this one is like a free edge, we call it. And this one with triangle shape is forced. Okay.
Okay, so they do not imply the left-off relation.
They also imply the left-out relation, but the left-out relation are fixed over all tilings. It doesn't depend on tilings. It only depends on the region.
Okay.
Okay. So maybe let me go on. Okay, so here is some other bijections might be interesting. It's just for the general information, and kind of I don't use them a lot. So the first one is acyclic orientations and hyperplane arrangement. There is some bijections, and I think Professor Zalewski make a lot of contribution in this area, and so the other two is about domino tilings. It has bijection with spanning trees on grid or perfect matching on grid. So for the this domino tilings is kind of so if you consider the dual of Z2 lattice, you will still get a Z2 lattice. But if you consider something else like a hexagon tiling, and its dual will be a triangular lattice. So people also interested in this part. Okay, but I don't do it. So maybe let me just go on. So here is part 2. I will introduce some known results and my interest. So any questions?
Yes, I'd like to ask you, was all this previous material known results?
You mean this page, right?
No, before this page.
Bijection.
Oh yeah, this one, all of this bijection is from Sheffield 2002.
Okay.
Okay, so all the previous work.
Thank you.
Okay, not my work.
Okay. It's pretty
Okay.
amazing.
Okay, so in part 2, I will introduce some natural questions and some known results. Okay, so people may ask some natural questions for ribbon tilings or some other objects. Say, does a region has a ribbon tiling? And then if it has, how many ribbon tilings of a region are there? And maybe a follow-up question, what does a random ribbon tiling of a region look like? Okay, so the first question is basically an existing problem. Second one is a counting problem. And the third one is a sampling problem. Here, sampling is, we are only interested in sampling from the uniform distribution. Okay, so here random, I mean from uniform distribution. Okay. Okay, and here is some known results. So first one is for domino tilings. So people have a formula to count domino tilings of rectangles. So this is the work from 1960s. And second, how to sampling a domino tiling is solved by Luby, 1995. And by the way, there are some other way to do it. So people also consider some other regions. So for domino tilings, so like this special diamond is like a diamond, but the boundary is kind of it's only horizontal and vertically. So but it doesn't matter for this talk. So let me skip it. And for so next for ribbon tilings, and the only thing we know for the previous natural questions is we know how to check whether there exists a ribbon tiling of simply connected region. Okay, so it's also basically from the work Sheffield again, 2002, the same paper, and previously we kind of construct the bijection with acyclic orientations, and this one could be done by using some conclusion from acyclic orientations or hyperplane arrangement. Okay, so here is something we know. Okay, so my interest, or our interest is we want to generalize the order not only for domino but for arbitrary order, and consider rectangular regions. Okay, so rectangular regions we consider so say a m by n rectangle. But m and n are much larger than the order n. Okay, and the other one is a special shape of rectangle. So basically, its width is the same as the order of ribbon tile. Okay, and so we call it a strip. All right, so we will study basically 4 parts. So counting for strips, sampling for strips, and talk about the growth rate. So basically, the growth rate here is when the rectangle region increases, and the number of tilings will also increases. And we are interested in how fast it grows. Okay, and at last, maybe a sampling from rectangle. Okay, so maybe I won't be able to talk all of them, so I will focus on the strip regions. Okay. But before everything, the first thing is a tellable condition. So for rectangles, so questions? Okay, no question. Oh, sorry. So let me go on. So for m by n rectangle, there exists a ribbon tiling if and only if n can be divided, n divided by capital M or n divided by capital N. Okay. This is not difficult. It can be shown using the definition of ribbon tiles. So basically, using this definition, you can basically count how many colors of basically you can count the colors of the region, and you just use this definition, you can show this. Okay. All right. And now, so before I talk about the have a question or not? No. Oh, sorry. Okay. So before we talk about the bijections between tilings and acyclic orientation of a graph. So now maybe it's interesting to see what this partially oriented graph looks like for rectangle. Okay, so to recover or maybe to construct this graph, it's sufficient for us to consider a naive tiling, say here, because from the work of Sheffield, it's only all these properties are invariant or are fixed for all tilings. So we only consider a naive one. Okay, so from here we can construct this graph in this way. And maybe more interesting to look at what the orientations of this false graph. So you will have always from this 4 to this red one and the other blue. So it's shown here, 4 is on the left of 1, 1, and 1, 1 is on the left of 4, 2. Okay. And you can do this similarly for 3, say 3, 2, 0, and 2 here. Okay. So basically you will have n isomorphic graphs here. Like, so basically the structure are the same. Okay. Yeah, and by the way, so before in the graph we mentioned about the boundary squares. So but here I said it can be removed. So because they didn't put any constraint on the free edges. For example, you have so some boundary square here, and you have boundary square here, and you see every tile is between them. So there's no tile between two boundary squares. Sorry, give me a moment. So yes, so all the relations are fixed. So basically you can simply remove all the boundary squares and it doesn't affect anything. Okay. So, okay, so let's move to the main part. Is my our contributions. Let's start with some warm-up examples. So consider a strip region. Strip region is like this. Okay, so it has naive tilings, and we can label the tile with its labels. With their levels. So 1, 2, 3, and so on. Okay, and we will denote the number of tilings using this F sub capital N. Okay, so this is basically what a strip look like. Okay, so let's start with the domino tilings. So I will show that the number of domino tilings is a Fibonacci sequence. It's also a known result. So the trick is we observe this square, how to cover it with a tile. And we have only two choices, either using a 0 tile or using a 1 tile. Okay, and if using a 0 tile, it turns out to be a strip with length n-1. So kind of you remove it and you only have this part left. Okay, and if you put 1 here, and for the bottom you have no other choices. You have to put a horizontal here, and it turns out to be a strip with n-2. Okay, so we have Fn equals Fn minus 1 plus fn minus 2. So Fibonacci. Okay. And next, let's consider an example a little bit more complicated. So with the same idea. So we still observe how to cover the left top square. So, and for n equals 3, we have 3 choices. We can use tile 0, tile 1, or tile 2 to cover it. So 3 cases. And for this case, it's already done. So done means we observe some recurrence here. It turns out to be a strip with length n minus 1. Okay. And for case 1 and case 2, we need to do something more. So start with case 1. So how to tell next one? So we have basically another 3 choices. We can put a 0 here. Okay. In this case, we are already done. We observe some recurrence. Okay. And we can also put a 2 in this way. And then in the following, 0 must be put here. No other choices. And then this part is also done. So it's a recurrence. It turned out to be a strip with length n minus 3. And then we could put 4 here. And in this case, after we put 4 here, we don't want to put 0 here. Okay, if we put 0 here, it turns back to this one. We don't want to recount it. So we have to put a 2 here, and in the following must be a 0. And then this one is also kind of a recurrence. Is come back to this case. Okay, you see this left boundary, their left boundary are the same. Only difference is their size. Okay. And for the last case is from this case 2, and we have 2 choices. We put 1 here or 0 here. If we put 0 here, is done. Is somehow a similar region with this case 1. Okay, and if we put 1 here, we don't have any other choice for the bottom one. So must be a 0 here, and then it turns back to be a strip. Okay, so by collecting all of these possible examples, we can write down a recursive system in this way. So basically, there are 2 regions will appear repeatedly. So we call them fundamental regions. So using sub 0 and sub here should be 1. Sub 1 to represent it. Here in the parentheses, n minus 1 is the size of this region. So originally it's size n, and we remove 1, so it turned out to be n minus 1. Here the same thing, we remove 1 and it turned out to be n minus 1. So using this notation, we get this recursive system, and it's kind of easy, very easy to solve. Okay. So after observe these 2 warm-up examples, let me just state my conclusion. So the conclusion in theorem 1, the number of ribbon tilings of fundamental regions satisfies the recursive system. So this is a matrix form, and the Fn is a vector, and it's the first the first element is just this Fn is what we want, is the number of tilings of a strip. Okay, and this vector is arranged in this way. So like so it in fact it doesn't really matter how you arrange it, but I just arrange it this way. Okay. Okay, the second theorem is about the property of An. An is this An here, is a matrix. So first of all, we will see that in the if you write down the recursive system, there will be n minus 1, basically n minus 1 factorial fundamental regions, and the order difference, difference order, I mean here. Here is n minus 1, n minus 2. In this case, it is 3, and in general, it will be n. Okay. And what's more is An has this form. I'll show you an example later. And here, this part is 0. Here and here are identical matrix. So question?
Other credit, term loans, etc., to the note that was made.
Sorry, could you say that again?
I cannot hear it.
Yeah, so I think someone have a question. So could you say that again? I can't hear it.
Maybe you're on mute or something.
So sorry, I don't know how to do it. So
I don't know who is asking. So
yeah, so okay, so maybe let me just go on. So if you have a question and I can't hear you, you can text me. All right. So and in the following, these following two properties may be important because I need to use it. So if we consider the eigenvalue of this matrix, so the largest eigenvalue is real and positive. Okay, and also the corresponding eigenvector could be also positive. Okay. Yeah. So basically, this matrix is very like I think like the transition matrix in Markov chain. But the only thing is for the transition matrix in Markov chain, we require the maximum eigenvalue equals 1. But here it can be lambda 1, can be greater than 1. Okay. Okay, and there are some other property, but I don't use it, so I skip it. Okay, and for the growth rate of Fn, recall Fn is the number of tilings of a strip. So we define the growth rate in this way. So take logarithm and divide it by n, and let n go to infinity. Okay, and this growth rate depends on small n, depends on the order of ribbon tiles. Okay, so my theorem, first of all, this limit, we need to talk about whether it exists or not. So I first show it exists, and then it can be bounded as follows. And for the left-hand side, using Stirling's approximation, we could get this approximation. Here is a small o n. Okay. All right. So basically, this will be my main conclusion about strip. So now let's start to show my idea how to prove them. So first of all, define what is the leftmost tile. So recall the example in domino and the case n equals 3. I kind of pick up some proper tiles in each step. So now I need to define it formally. So suppose you have a tiling of a region, and then you will have a cyclic orientation of the corresponding graph. So, and in that graph, we define a source tile is the source in that cyclic orientation. Okay, so, but you could have many sources, and we just pick up the one with smallest level and call it the leftmost tile. Okay. So this is how I define leftmost tile, and it must be exist and unique. Okay, and then what is the leftmost tiling process? So for untiled region, we could declare a proper tile to be the leftmost, right? So if you consider the cyclic orientation, is you have a graph. And you can pick up a vertex and say that one will be a source, right? And put the proper orientations on that graph. Okay. So this is how I define the leftmost tiling process. And the observation is the okay. So the tiling sequence is the basically a sequence of tiles satisfy the leftmost tiling process. And it's bidirectionally correspond to ribbon tilings. So if you have a tiling sequence, you can recover a ribbon tiling. Okay, and of course, if you have ribbon tiling, you can write down the tiling sequence. Okay, okay. So, but in principle, for the leftmost tiling process, you can stop in any steps. Okay. So if you stop earlier and you have a current tiling sequence T, I just denote RT to be the residual region. So basically, it's the remain region. Okay. The region haven't been tiled. Oh, okay. Okay. So so next, it's important to know what are the proper size, proper tiles in each step of the leftmost tiling process. So let's start with some notations. I need this notation to talk about my lemma. So X is the tiling sequence, current tiling sequence that has been declared. For example, in this plot, you have 2 and 1 is X, okay? So Y is the remaining labels, so is the tiles we will use to tile this region, okay? And clearly X union Y is the whole label side, okay? And W sub X is the last element of the sequence X, and W maximal X is the maximal label in X. So in this example, 1 is W sub X, and 2 is W maximal X. So they could be different. Okay. So using these notations, let's start with some examples. So suppose we want to say W is a leftmost tile. So then clearly in the first step, 0, 1, 2, 3 is our possible choices. And then you need to satisfy some requirement. First of all, W minus N is not in Y. So C, B, 5 is possible only because we have already put 1 in X. We declare 1 is the leftmost in the previous steps. So then 5 become a possible choice. Okay. So the second item, W is greater than WX minus N. So let's see this example in C. So we say 0 is not a valid candidate since here WX is 5 and the 5 minus order is 4 is 1, so greater than 0. So 0 is not a valid choice. Okay, and the third item is W maximal X plus N is greater than W. So basically this just say you cannot have something far away from the previous steps. Okay. Okay. So and I define C bar to be the side of tiles satisfy these 3 conditions. All right. So, but you may also note that here 9 is also not a valid choice, but I will explain it in the next page. Okay. Okay, here, okay. In this example, 7 and 9 are not candidates since it's too far away from the previous element in C bar, okay. So for example, here they are too far away, and here the same thing. Too far away means their difference is greater than N, okay. So I define C in this way. First order C bar as an increasing sequence, and we stop as I. I is the index such that I plus 1 minus Wi is greater than N. So basically, just say it's cannot too far away. Okay. So now I'm ready to say my lemma. So basically, it's at each step, a tile is a candidate. So if and only if W is in C, basically we know the candidate set C. Okay, and the proof is very routine. So basically you can prove everything by contradiction with a cyclic. Okay. So but this lemma is very useful. So we know how to in each step what kind of candidates we have. We can list all of them, and in this way we are able to enumerate all tilings. Okay. Okay. So next I'll talk about 2 properties of tiling sequences. So say J is a tiling sequence, then and J prime is a permutation of J, but J prime is also a valid tiling sequence. Then their residual region are the same. Say from this picture, J is 1, 5, 2. So and here its permutation could be 1, 2, and 5. And you see these two regions are the same. Two residual regions are the same. Okay. And second item is if pi permutes. So again, J is a tiling sequence, and if pi permutes J as an increasing sequence, then pi J is a valid tiling sequence. So like here, 1, 2, 5 increasing, and it's a valid tiling sequence. Okay. So now we know how to do the tiling sequence. We also need to observe some recurrence. So, and the recurrence happens when 0 square is covered by a tile. So, and we call it as a deducting moment. So deducting moment basically is you run the leftmost tiling process, and in some step 0 is declared to be the leftmost. Okay, and we say at this moment, we say if a column is fully covered, we call it full columns. And this one, we say J in this way achieves the deducting moment with D equals 4 full columns. Okay. So basically next, we want to remove this 4 and get some recurrence. So before that, let me introduce some operator. So first one is zeta. Basically zeta, you can imagine this T is just 0. Pull this T out and put it at the beginning of the sequence is zeta. I call it return operator. And this lemma for this operator basically say the return operator make the valid tiling sequence still a valid tiling sequence. Okay. But the condition is T can be the leftmost tile. So in our example, 0 of course can be the leftmost tile of a region. Okay. So let me skip the proof. And next I'll introduce another operator called delta. So questions? Okay, so let me keep going. So this called deduction operator. So basically, if a sequence starting with 0, I just remove this 0 and everybody minus 1. So it's called deduction operator. Okay. So for example, here, deduction operator basically just remove the first column, and what's left are the same, basically the same tiling. You just label it differently. Okay. Okay. So now I use these two operators to define fundamental sequences. So say if this tiling sequence J achieves the deducting moment 0 here, and with D equals 4 full columns, and I use the operator zeta 0 and delta D times and on J. And finally, I permute the result as an increasing sequence. Okay, so for example, here, after this operator, basically what I did is just remove these 4 columns, and the tiling will be 1, 2, 5. So you're using these operators on J, you will have this result, F. Okay. So, and this F is well defined since I proved that if the permutation of the sequence are the same for its residual regions. So RF is well defined. And the regions, say if the left boundary is the same as F, but the size difference will appear repeatedly in the leftmost tiling process. So this will tell us some recurrence here. Okay. So Here is an example for n equals 4. So this is all fundamental sequences of n equals 4. So we will have 6 in total, and 6 here is n minus 1 factorial. So okay, so that's an example. And here I cheat a little bit. So this guy is supposed to be an empty sequence because you know 0, if you put 0 here after the operator, you will get empty sequence, but empty just looks ugly. So I use 0 to represent it. Okay. So next I will introduce another construction for fundamental sequences because the previous one is motivated by recurrence, but it's very difficult to say any properties about the fundamental sequences. So I define a boundary sequence and try to build a bijection between them. Okay, so boundary sequences basically is sequences horizontally satisfy these conditions, and B0 is always start with 0.
So in the first condition, it seems bk minus 1 plus, and after that nothing. So
you mean?
Yeah, the first one, bk 1 plus.
Yeah.
Should be 1 or what? Nothing, no plus.
Yeah, I think 1. Yeah,
Okay.
yeah, should be 1 here. Okay, sorry. Yeah. Okay. So in this example, A and B are valid boundary sequences, and C and D are not. Okay. So C is not, since this 4 equals 0 plus n. Okay, it doesn't satisfy the second condition. Okay, so for L equals 1 basically, and for D, 9 is not valid because 9 doesn't satisfy the first condition. So it's too far away. So it might be something closer. For example, here. Okay, so this is basically how I define boundary sequences. Okay. And okay, so again, an example of all boundary sequences for n equals 4, at least all of them, and kind of, I don't know why this happened. So it kind of has a bijection with the fundamental sequence you can see from these pictures. Okay. So to show that, I'll define a map sigma, so very naturally, and show that this one is a bijection. Okay, so but maybe let me skip the details of this. So now let me give a short summary so far what I have done. So we define the leftmost tiling process, and it can be used to enumerate ribbon tilings, and we know the candidate site of each step. And then to observe recurrence, we define fundamental sequences. So the definition is motivated by recurrence. And I introduce another description of fundamental sequence. So this is boundary sequences. And using this, we can show a lot of properties of fundamental sequences. Okay. So basically, we collect everything of fundamental sequences. And next stage is we need to study the relations between those fundamental regions or fundamental sequences, and using this relation to generate the recursive system. Okay. So basically, we need this. I call it tiling transition. From F to F prime is from one fundamental sequence to another, so defined in this way. So for case 1, so you start with F and you keep going with the leftmost tiling process. If F and J together is a fundamental sequence, then you are done. So this is F prime. Okay. In the other case is F and J together achieve the deducting moment shown in the below picture, and in this way you just deduct it to be a fundamental sequence. Like here, say F is 1, 2, 5, and you start with f, you keep going, and j equals 3 and 0, and using the operator zeta, delta, and pi, you will get only 1 left. So f prime equals 1, f equals 1 to 5. So this is a transition. Okay. So this is a lemma for this transition. Basically, say this transition is unique. Unique regarded as j. So if f and f prime are fixed, and j is uniquely determinant. Okay. So basically, it's unique, and it guarantees us we can write down the recursive equations to for the number of tilings. Okay. So now basically we have the theorem 1 by the previous lemma. So all the fundamental regions, if we count them, they satisfy this recursive system. Okay. And these properties, we have n-1 factorial fundamental regions is obtained by study the boundary sequences. Okay. Okay, and here is an example of A3. So the case
essentially, you have an effective way to kind of list all the fundamental regions, right?
So you mean using boundary squares?
Boundary sequences, yes.
Yeah. Using boundary sequences will be more efficient. Yes. If your n is really large. But if your n is really large, and then this matrix will be dimension n factorial, so it's difficult to calculate it. Okay, so in my algorithm or my programming, the time issue happens when I try to do the eigen decomposition of this matrix. So everything before is fine. Okay. So A3, for example, looks like this. This part is 0. Here's identity. Here's identity. Okay. So maybe a summary to how I get this matrix AN. So I could run the leftmost tiling process and collect all fundamental regions. Or as Professor Kargin said, I can also using boundary sequences to build it. After this, I just run this process again, starting from each fundamental region, and we can generate the recursive equation and write down the matrix A. And next thing is just solve this equation, recursive system. So basically, it's just calculate the power of this matrix. Here is some numeric result. So this 1, 2, 3 is the length of the strip up to 10. And here is the order of ribbon tails. So the result I have is, just like this. Okay. And some other interesting properties say is the maybe eigenvalues of AN. So this plot is this black dot is eigenvalue on the complex plane, and this blue line is so-called hypercycloid. So you have this interesting shape, but unfortunately, I don't have any explanation for this. Okay, so just show the picture. Okay, so next is sampling ribbon tiling of a strip. So recall that in this theorem, we could calculate all the number of tilings for each fundamental regions. I will use this result. It's kind of very strong. So and sampling makes sampling very easy. So basically, if we consider a domino tiling, in this case, we know exactly the probability we should put on each case. So for example, if we want to generate a sample from the uniform distribution, we need to put the probability fn-1 over fn. And in this case, since it will turn out to be a strip with length n-2, so it's a proportion to fn-2. Okay, so using this idea, we just know how to do it with this probability, put this probability on. Okay, so maybe let me ignore these details. And yeah, maybe by the way, this will be interesting to consider asymptotic property, because this the ratio of the number of tilings of each fundamental region is really determined by an, the matrix an. And here lambda 1 is so it is a largest eigenvalue, and this U1 is the corresponding eigenvector, and U1, small U1 and U2 is the element of U1. So you know the matrix of an, you know everything about this, and so you don't really need to count the number of tilings. You can just use this ratio, and it will be proportional to this probability. So you can sample it. Okay. Here is some result of sampling. So maybe a little bit messy. So here I use polyline to indicate a tiling. So, and I can show you later that the tile is kind of easier to go to right. So because you know, recall that for ribbon tile, each step you can go either up or right. So from random sampling, it's easier to go to the right. Okay, so questions?
I have a question about your previous slide.
Okay.
Yeah, that limit. Okay, I'm having a trouble keeping track of. Okay, so we've got this. What are the things we're treating as sort of easy to calculate, and what are we treating as not easy to calculate? Because AN could be enormous. So are we saying n is small enough that we can find lambda 1 from AN?
Yes.
Okay. All right. Yeah. So we can calculate that limit. So we use AN to get the right-hand side of the equation.
Yes, yes.
Okay. All right.
So if you want to call it the number of tilings, you need to call it the power of AN. So here I just say you don't need really to call it the power. You can just use this.
Okay. All right. Thank you.
Okay. So I mentioned just now, you can see some easier trend to the right. So, but I will show you maybe more clearly. So make some statistics. I call it the frequency of each type of tiles. So this 0 means a tile vertically always go up, and here the largest one in x-axis means the tile always go to the right horizontally. Okay, and if you call it the frequency, you will see these pictures, and you may see some shake here. Is just because some symmetric tiles need to be identified. So like here, this tile n equals 3, this tile means you go up and right. So this one means you go right first and up. So they are symmetric, so it's supposed to have the same frequency. Okay. So next, what I will do in the next picture you will see is I identify these two types of symmetric tiles, and it gives us this picture. So for example, here I identify those two, and it's almost overlap with each other. Okay, and in this picture, we see a kind of upper trend more clearly. And the color.
What does it mean that it goes, what it means that it's to the right?
To the right means, for example, here is a horizontal tile. You have more horizontal tiles compared to vertical ones.
More horizontal steps. Okay.
Yeah, horizontal steps. Yeah, and the color means how many steps you go to the right for the tile. Okay, so you see the color somehow together. Okay.
What is the vertical axis?
The frequency.
It's not from 0 to 1, though.
It's yeah, but it's supposed to be 0 to 1. But maybe you submit this, it will be 1.
I'm sorry, what?
So if you submit all of this, it will be 1.
You add up all these numbers, I think. If you
What?
add up all these numbers, it will be 1. So
If
it
you
just,
do what?
it will be 1. So it just
How do you get 1? I don't know what you're saying.
So you add up these numbers, it will be 1.
I'm talking about the vertical scale.
yeah.
Yeah.
Probability that you'll find the probability that you find a tile, as far as I understand, right?
Yes,
Okay,
yes.
it's a probability that you'll find a certain tile, and it is not from 0 to 1, so it's been truncated, which gives a possibly misleading impression of the size. I know why you do this, because you save space.
Yes, because when, for example, when n equals 8, you will have n to the power 7 types. It will be too much. So this will make this scale very small. So if I put everyone in the same scale, you won't able to see any difference here.
Okay, so what happens is that the vertical scales are completely different on the different graphs, but they're shrunk so that they fit the same size
Uh,
or expanded, whatever.
yeah,
It's
but
very hard to read this. I'm sorry. It's hard for me to read this, I should say, because it's so small.
yeah, it's so small since the type is too much.
I understand.
Yeah, so, yeah, n say 2 to the power 7 is a big number, so that makes this one very small.
Well, that doesn't matter. No, the point is that it's hard. No, it's hard for me to see the numbers because they are small numbers. They are small size symbols and they are tilted to the side.
Okay, so sorry.
That's okay. You couldn't help it.
Okay. Okay, so yeah, maybe at least I make my point clearly. So, you know.
Yeah. I understand.
Okay.
But I tried to understand what these pictures are showing. Thank you.
Okay. Thank you, Professor. Okay. Okay, let's move on. So next I'll talk about the growth rate. Okay, so first of all, let me define the growth rate. So recall we have Fn is the number of tilings of strips. So I take logarithm and divide it by capital N, the size of the strip, and take the limit. And this is defined as the growth rate. Your question? Okay, so for example, for domino tilings, Fn is a famous Fibonacci sequence, and this is well-known result. This ratio, as n goes to infinity, will be the golden ratio. Okay, so the connection with the growth rate I define is just take the logarithm, and it will be like this. Okay, so we will consider arbitrary n, and we have basically two questions. First of all, whether this limit exists or not. And the second one is how can we bound it? So it's in this theorem. So this growth rate exists and bounded in this way. So on the right, upper bound is log n. On the left is log n. Sorry, I think I missed the nth root of log n. Sorry. And using Stirling's approximation, the left-hand side will be log n minus 1, and the right-hand side will be log n. Okay, so this is the bound I gave. Okay, so yeah, maybe I think I still have some time to explain it. So to prove the existence, we observe the superadditivity. So we can separate the strip into two regions, N1 and N2. So just observe that for the tilings of N1 and N2 together is a tiling of the whole thing. Okay, so then we have this inequality. And then if we take logarithm, it will be superadditivity. And for superadditivity, we can use Fakir's lemma. It basically say if something satisfies superadditivity, and you divide it by n and take this limit, will be supremum of this guy. Okay, but note that the supremum could be infinity. Okay, so this is basically Fakir's lemma talked about. And in our case, we can give a bound of Fn very easily because we have n tiles And for each tile, we have n2 to the power n minus 1 types. So in total, we have this upper bounded for Fn. So since it's upper bounded and is the supremum is the upper bounded, so it must be some constants. So the growth rate exists. Okay. So for the lower bound, maybe observe the fact that the n by n square, you have only, you can count it very easily. It's just n factorial number of tilings. Just is correspond to a complete graph with n vertices. Okay, and this will give us the lower bound of Fn. Okay, and for the upper bound,
I think that you should say that your previous upper bound was very rough. It was much worse than in your theorem.
Yes, yes. Thank you. So this upper bound, if you take logarithm and divide it by n, you will have log 2 to the power n. So it's kind of exponential. So I will, yeah. So I'm talking about here is a much better upper bound. Okay, using this key argument. Okay. So to prove this, basically we consider T and T0. So T is the size of all tiling sequences, and T0 is all tiling sequences starting with 0. And we build a map zeta 0 from T to T0. And for each element, for each tiling sequence in T0, we consider its inverse map, and it will be C, a subset. So, okay, so it will be a subset of T, and this C is a component of T. Okay, and the main job we need to show is the size of C is less than or equals to n. Okay, so and how to do this is we consider this J is ordered, is fixed ordered sequences, and starting with 0, and we just, how do we recover C? We just ask ourselves the question, where can we put 0 in that sequence? And then by the definition of the leftmost tiling process, 0 can only follow the tile 1, 2, 3, and up to n minus 1. Only have this n minus 1 choices, and including the putting the case that putting 0 at the beginning, you will have totally n choices. So this is how I upper bound it. Okay. So using this key argument, we can get some induction. So and Fn will be less than or equals to so I think I show it here. N to the power capital N. So just using the previous argument. And with this lower bound and upper bound, and by definition, I take logarithm and divide it by capital N, I will got this. So again, here I miss it. Okay. Okay, so next is some numerical result. So these circles are the number of tilings for different lengths n. And this horizontal line is lambda 1 for the matrix. Okay. First of all, you see that it's convergent, and it seems like if your n order n getting bigger, the it converges slowly. And the next plot is the growth rate. So the black point is the growth rate, and the red and blue line are the upper and the lower bound I provide in the theory. But here 1 is interesting. So unluckily it's consistent here. So 1 is, so what is order 1 ribbon tiling? So it's just square. And the corresponding strip is just a 1 by capital N region. And then you have only one way to tell it. And so the growth rate is just 0. So luckily it's consistent here. Okay, so here is some numerical result. Okay, so now I would like to generalize it to rectangles. Okay, so I define gamma. So first of all, F sub capital M and N will be the tilings of this rectangle, and the growth rate is defined this way. So log divided by the size of this region. The size is just the number of tiles contained in this region. So I call this gamma n. So still two questions. So the limit exists or not, and how can we bound this gamma? Okay. So to prove existence, we first of all observe the superaddivities. So in such a way, it can also two-dimensional, but the argument is the same. So you have several small regions, and the tilings of them together is the tiling of the big region. So we have this superadditivity. Take logarithm, it will be additivity. And then I prove this two-dimensional Fakir lemma using very similar argument as the proof of Fakir lemma. So to show that this limit is just the supremum of this guy, and this supremum could be constant or infinity. Okay, and we can use a very loose upper bound to bound it. So and immediately we got this limit exists, right? So gamma n exists, and to show its upper bound, the key argument is this way. So it's also the similar idea with the strip. So, but before it's n, here is this kind of thing. And k is equals m divided by small n. So since I showed that, so for a rectangle, if it has a tiling m, n divided by m or n divided by n, capital N. So here I just suppose n divided by capital M. So k is integer. So in this case, k equals 3. Okay. So before we consider the map zeta 0. So here similarly we define zeta s, and it also introduce a component c, and we try to show that the side of c is less than or equals this quantity here by using like long-run multiplier. So it turns out I write it turned out to be a maximal problem, and try to solve it using long-run multiplier. Okay, so but maybe I skip it. Okay, so next part is sampling ribbon tilings of a rectangle. So maybe I just mention it a little bit. We can have a very good method for the strip, since we can count all the fundamental regions. But here for rectangles, we don't have that kind of conclusion. So the method we use is the Markov chain method, Markov chain Monte Carlo method. So I define so the updating mechanism this way. So it's a long word. So the thing is, it's now difficult to show this defined chain is will convert to uniform distribution. What the difficulty is show is mixing time. So I don't have time to talk about what is mixing time. But the thing is, we want it to be a rapidly mixing by showing that the time is polynomial of the size of the region. Okay, so still a lot of things could be done in this part, but since the time limit, so I guess I just stop here. Okay, so sorry. So for the future work, so there are some possible extension of the current work. For example, so can we explain the funny shape of the eigenvalues of AN? Okay, so and also can we have a better upper bound for the growth rate of the rectangle region, general rectangle region? Okay, so this is some possible extension of current work. And the other thing is the bijections and conformal invariance of height function. I didn't mention height function, but height function is also a very important part for the ribbon tilings. So any bijection or conformal invariance of height function might be interesting. And in general, I think I also interested in the conformal invariance and the bijections. in other objects, not only for tilings or ribbon tilings. So it's maybe the future work I plan to do. So, okay, so basically thanks everybody. So I stop here. Okay, so maybe any questions?
I guess I have a question.
Yeah, sure.
Yeah, okay. I think you may have almost answered this. I haven't just put it all together in my head. So once again, you have A sub n, which is this huge matrix. But then you did these limit thing. So if you had to calculate its dominant eigenvalue directly when n is large, that wouldn't be doable. You did those limit things, and did that essentially calculate the dominant eigenvalue?
Yeah. There are, yeah.
So may I ask you, when you're saying limit things, you mean about the growth rate, the bounds on the growth rate?
Yeah, I guess so.
It's not from AN. It's not from this matrix.
It's not from the matrix, but that's what I'm saying, is that you can get to the dominant eigenvalue without going through the matrix.
No, it's not possible to figure out what's the dominant eigenvalue from the matrix. No, it's a
no. I'm not saying. That's what I'm saying. You're not using the matrix. Yes.
No.
Yeah. Okay.
No. I'm. Yeah. Okay.
Yeah. Thank you.
Can I ask what you mean by conformal invariance of height function?
Okay.
What is conformal invariance in this context?
Yeah. So conformal just means conformal mapping in just the in complex analysis. So invariance is a very not rigorous word. So invariance is just some properties may hold the same. So you map one thing to the other thing. So, so I don't have any concrete example here, but yeah, it's a kind of could be a big area, or a lot of things could define here, but I just interested in general.
Are you saying that a height function is a complex function?
No, height function is defined. I didn't mention it, but it's related to tiling. So you basically different tiling correspond to different height function.
I think he means. I think he means. So there's a real part of some complex function. It's not complex, but it's a real part of the complex.
Yeah.
Is that what you mean?
Yeah.
Yeah, and not and discrete variant of the discrete.
Yeah, discrete case. Yeah.
Then go to continuous. Yes.
Yeah, you could go to you let let's go to infinity and you get some continuous case. Yeah.
Okay, thank you.
All right.
Okay. So any more questions?
Well, so if no more questions, maybe kind of we could go to the other stage of this seminar. So I mean, then just committee discusses.
Okay.
The committee could go to a breakout room.
If I knew how to do it, I would breakout room.
Actually, a committee member can just leave now, and then you can, if for